According to NFPA 20 and NFPA 70, the cable size should be determined based on the maximum full load starting current of the motor, which in this case is 600 amps for direct online connection. Use Table 310.16 of the National Electrical Code, or NEC, to determine the minimum allowable American wire gauge, or AWG size for a copper conductor carrying 600 amps. For 75 degrees Celsius conductors, the required American wire gauge size is 4/0. Multiply the American wire gauge size by 2 to obtain the conductor size in thousands of circular mils, or MCM. Therefore, the cable conductor size should be 500 MCM. Determine the motor protection factor, or MPF, based on the motor starting method. For direct online starting, the motor protection factor equals 1.15. For all other methods, the motor protection factor equals 1.25. Calculate the circuit breaker rating using the following formula. Circuit breaker rating equals motor protection factor times motor full load current. For direct online connection, circuit breaker rating equals 1.15 times 600 amps, which equals 690 amps. Determine the switchgear rating based on the circuit breaker rating and the applicable NEC requirements. For industrial applications, the switchgear rating should be at least 1.25 times the circuit breaker rating. Switchgear rating equals 1.25 times circuit breaker rating. For direct online connection, switchgear rating equals 1.25 times 690 amps, which equals 862.5 amps. Note that the cable size and circuit breaker rating should be increased if the motor is operating at an elevated ambient temperature or if the cable length exceeds the manufacturer's recommendations. The switchgear should be selected to meet the specific requirements of the application, including voltage rating, interrupting capacity, and short-circuit protection. It is advisable to consult with an electrical engineer for proper sizing and selection of materials. To elaborate on cable sizing, we need to consider several factors beyond just the ampacity from NEC Table 310.16. Firstly, correction factors for ambient temperature play a crucial role. The ampacity values in Table 310.16 are based on a specific ambient temperature, typically 30 degrees Celsius or 86 degrees Fahrenheit. If the actual ambient temperature where the cable is installed is higher, the cable's ampacity must be reduced by applying the appropriate correction factor from the table associated with 310.16. Secondly, adjustment factors for the number of current carrying conductors in a raceway or cable need to be accounted for. When multiple current carrying conductors are bundled together in a raceway, cable tray, or direct buried, the heat generated by each conductor can raise the overall temperature, reducing the ampacity of each conductor. NEC Table 310.15 current provides adjustment factors based on the number of current carrying conductors. For example, if there are 4 to 6 current carrying conductors, the ampacity is adjusted to 80% of the value in Table 310.16. Thirdly, voltage drop is a significant consideration, especially for long cable runs. Excessive voltage drop can cause motors to operate inefficiently, overheat, or even fail to start. The NEC recommends limiting voltage drop to no more than 5% from the source to the furthest motor. Voltage drop can be calculated using formulas that take into account the cable length, current, conductor resistance, and voltage. If the calculated voltage drop exceeds the recommended limit, a larger cable size may be necessary. Fourthly, conductor material is a key factor. Copper and aluminum are the most common conductor materials, each with different ampacity ratings. Copper has a higher ampacity than aluminum for the same size conductor. The choice of conductor material depends on factors such as cost, weight, and environmental conditions. For fire pump applications, copper is generally preferred due to its superior conductivity and corrosion resistance. Fifthly, insulation type affects the cable's temperature rating and ampacity. Common insulation types include THHN, THWN, XHHW, and RHW. Each insulation type has a different maximum operating temperature, which affects the cable's ampacity. For example, THHN and THWN conductors are typically rated for 75 degrees Celsius in wet locations and 90 degrees Celsius in dry locations, while XHHW conductors are rated for 90 degrees Celsius in both wet and dry locations. The higher the temperature rating, the higher the ampacity. Sixthly, insulation method impacts the cable's ability to dissipate heat. Cables installed in free air have a higher ampacity than cables installed in conduits or direct buried. The NEC provides different ampacity tables for different installation methods. For example, Table 310.16 applies to cables installed in raceways or direct buried, while Table 310.17 applies to cables installed in free air. Seventhly, the motor's nameplate full load amps, or FLAW, is the starting point for cable sizing. The NEC requires that the cable ampacity be at least 125% of the motor's FLA. This provides a safety factor to account for motor overload and starting currents. Eighthly, the motor's service factor is a multiplier that accounts for the motor's ability to operate continuously at loads higher than its rated horsepower. If the motor has a service factor greater than 1.0, the cable ampacity must be increased accordingly. Ninthly, the motor's code letter indicates the motor's locked rotor amps, or LRA, which is the current the motor draws when it is first started. The cable must be able to withstand the motor's LRA without being damaged. The NEC provides tables that relate motor code letters to LRA values. Tenthly, the available fault current at the motor location must be considered. The cable must have a short circuit current rating that is high enough to withstand the available fault current. If the fault current is too high, the cable may be damaged or even explode. Regarding circuit breaker sizing, several factors must be considered to ensure proper motor protection and coordination with the electrical system. Firstly, the NEC provides specific guidelines for sizing motor circuit breakers in Article 430. These guidelines are based on the motor's FLA, service factor, and code letter. Secondly, the circuit breaker must provide both overload protection and short circuit protection. Overload protection protects the motor from overheating due to excessive load, while short circuit protection protects the motor and the electrical system from damage due to faults. Thirdly, the circuit breaker must be able to handle the motor's starting current without tripping. Motors draw a high inrush current when they are first started, which can be several times the motor's FLA. The circuit breaker must be able to withstand this inrush current for a short period of time without tripping. Fourthly, inverse time circuit breakers are commonly used for motor protection. These breakers have a tripping characteristic that is inversely proportional to the current. This means that the breaker will trip quickly for high currents such as short circuits, and slowly for lower currents such as overloads. Fifthly, instantaneous trip circuit breakers are also used for motor protection. These breakers trip almost instantaneously when a high current fault is detected. Instantaneous trip breakers are typically used in combination with inverse time breakers to provide both overload and short circuit protection. Sixthly, the circuit breaker's interrupting rating must be high enough to interrupt the available fault current at the motor location. The interrupting rating is the maximum current that the breaker can safely interrupt without being damaged. Seventhly, the circuit breaker's frame size must be large enough to accommodate the required current rating. The frame size is the physical size of the breaker, which determines the maximum current that the breaker can carry. Eighthly, the circuit breaker's trip unit must be properly calibrated to match the motor's characteristics. The trip unit is the electronic component that controls the breaker's tripping characteristics. Ninthly, motor starter overload relays are used in conjunction with circuit breakers to provide additional motor protection. Overload relays are designed to protect the motor from overheating due to prolonged overloads. Tenthly, coordination studies are essential to ensure that the motor circuit breaker is properly coordinated with other protective devices in the electrical system. Coordination studies help to ensure that the breaker closest to the fault will trip first, minimizing the impact on the rest of the system. When selecting switchgear, several factors must be considered to ensure safe and reliable operation of the electrical system. Firstly, the switchgear must be rated for the voltage and current of the system. The voltage rating must be equal to or greater than the system voltage, and the current rating must be equal to or greater than the maximum current that the switchgear will carry. Secondly, the switchgear must have an interrupting rating that is high enough to interrupt the available fault current at the switchgear location. The interrupting rating is the maximum current that the switchgear can safely interrupt without being damaged. Thirdly, the switchgear must be designed to withstand the environmental conditions at the installation location. This includes temperature, humidity, and altitude. Fourthly, the switchgear must be equipped with the necessary protective devices such as circuit breakers, fuses, and relays to protect the electrical system from overloads, short circuits, and other faults. Fifthly, the switchgear must be designed to provide adequate ventilation to prevent overheating. Overheating can damage the switchgear components and reduce its lifespan. Sixthly, the switchgear must be accessible for maintenance and repair. This includes providing adequate space around the switchgear for personnel to work safely. Seventhly, the switchgear must comply with all applicable codes and standards such as the NEC, ANSI, and IEEE. Eighthly, the switchgear must be properly grounded to provide a safe path for fault current to return to the source. Ninthly, the switchgear must be equipped with the necessary metering and monitoring devices to provide information about the system's performance. This includes voltmeters, ammeters, and power meters. Tenthly, the switchgear must be designed to be easily expandable to accommodate future growth of the electrical system. Specific requirements for fire pump applications based on NFPA 20 and NFPA 70 add another layer of complexity. NFPA 20, the standard for the installation of stationary fire pumps for fire protection, has specific requirements for the electrical supply to fire pumps. Firstly, the power source for the fire pump must be reliable and independent of the normal power source. This is typically achieved by using a separate service or a generator. Secondly, the fire pump circuit must be protected by overcurrent devices that are sized to allow the fire pump motor to start and run without tripping. The overcurrent devices must be able to carry the locked rotor current of the motor for a specified period of time. Thirdly, the fire pump circuit must be designed to minimize voltage drop during motor starting. Excessive voltage drop can cause the motor to stall or fail to start. Fourthly, the fire pump circuit must be supervised to ensure that it is always ready to operate. This includes monitoring the voltage, current, and phase rotation of the power supply. Fifthly, the fire pump controller must be listed for fire pump service and must comply with the requirements of NFPA 20. Sixthly, the wiring for the fire pump circuit must be protected from physical damage and fire. This is typically achieved by using rigid metal conduit or mineral insulated cable. Seventhly, emergency power systems for fire pumps must comply with NFPA 70, the National Electrical Code, and NFPA 20. The emergency power system must be capable of providing power to the fire pump for a specified period of time, typically 2 hours. Eighthly, transfer switches for fire pumps must be listed for fire pump service and must comply with the requirements of NFPA 20. The transfer switch must be able to automatically transfer power from the normal power source to the emergency power source in the event of a power failure. Ninthly, fire pump rooms must be properly ventilated to prevent overheating. The ventilation system must be designed to remove heat generated by the fire pump motor and controller. Tenthly, periodic testing and maintenance of the fire pump system are essential to ensure that it is always ready to operate. This includes testing the fire pump motor, controller, and power supply. In summary, calculating the cable size, circuit breaker rating, and switchgear rating for motors, especially fire pump motors, requires careful consideration of various factors, including motor characteristics, ambient conditions, installation methods, and applicable codes and standards. Consulting with a qualified electrical engineer is highly recommended to ensure that the electrical system is properly designed and installed. Remember to always prioritize safety and adhere to the latest edition of the NEC and NFPA standards.